Composite functions are made up of two separate functions where you've taken one and stuck it inside of the other. I like to think of sushi, where you use the same two ingredients to create different dishes, like sushi rolls or nigiri. In one case, the fish is on the inside of the rice, and on the other, the fish is on the outside of the rice. So using the same two functions, so to speak, you can create two different composites. Let's take a look at limits of composite functions. The composite function theorem says that if you know the limit of a function, say g, and you're going to stick g inside of another function, call it f, and you know that f is continuous for the outputs of g, then you can basically sneak the limit inside of the outer function. Basically, what we're saying is you're going to evaluate the limit on the inside function first. Whatever that limit is equal to, you're going to evaluate the outer function at that limit value. Let's take a look at an example. If we want to look at the limit where x is approaching pi over 2 for the function cosine of x minus pi over 2, we can consider the x minus pi over 2 the inner function, like the g of x. And we can evaluate the limit of that inner function as x is approaching pi over 2, and we see that that would be equal to 0. That is the limiting value of the inner function. We know that cosine is continuous at 0 because the limit as x approaches 0 for cosine is exactly equal to cosine evaluated at 0. So we can call cosine our outer function, and we're going to evaluate that at the limiting value of g, which is 0. So using the composite function theorem, we can evaluate this limit by considering the outside function and the inside function, sneaking the limit inside of the outer function, evaluating the limit on that inner function, and then finishing it up by evaluating our outside function at that limiting value. So this composite function theorem is pretty straightforward. It's almost like our limit laws, where you're allowed to now move the limit operator inside of a composition of functions, and this is useful for showing that our trig functions are continuous. Maybe we're curious, is the trig function cosine x continuous everywhere? Looking at the graph, we would think, yeah, probably. But we have to check our continuity conditions to be able to conclude that this is true. Showing that cosine is continuous at a single point is not the same thing as showing that cosine is continuous everywhere. If we want to show it's continuous everywhere, then we have to use a generic value a that is inside of the domain of cosine x to show that our continuity conditions hold up. Let's take a look. We'll start by considering the limit as x is approaching some value a for the function cosine x. Now cosine x has a domain of all real numbers, so a could be any number you want. Big, small, positive, negative, anything. Our first step is to rewrite x inside of the cosine function as x minus a plus a. And we can do this because subtracting and adding the exact same value is almost like nothing ever happened. It's like a 0. Next, we're going to apply the cosine sum of two angles identity. We're going to split the x minus a plus a into two groups. X minus a will consider one group, and the plus a will be its own separate group. And that way we can use this sum of two angles identity. So rewriting our cosine of x minus a plus a using this identity, we now have multiple terms that we can apply the limit laws to. Once we take the limit of each term, now we can see that we have some composite functions. So cosine of x minus a, that's a composite. Sine of x minus a, that's a composite. So we'll apply the composite function theorem. We'll allow those limit operators to sneak inside of the outer functions. Now we're ready to evaluate. Evaluating each limit one at a time. And then simplifying. We just showed that for any a you can imagine, the limit of x approaching a for the function cosine x will always be equal to cosine a. That is the definition of continuous. We showed that not only does the function exist at a, because a is in the domain of cosine, but that the two-sided limit exists and that that two-sided limit is equal to the function output at a. We could repeat this process for any trig function actually, and we'll show that they're continuous. So cosine and sine are continuous. Tangent is continuous within a restricted domain, but you can repeat this process where you put the condition on a that it has to be within that restricted domain to show tangent's continuous over its period.